In this lecture, we shall give another example of a proof by induction, proving a statement that refers to divisibility on natural numbers. We shall prove for all natural numbers n that n cubed plus 2n is divisible by 3. And we shall see that induction is a convenient proof technique to deal with the universal quantification over all natural numbers in this statement. The predicate we want to prove involves divisibility. We want to give a proof that only relies on some elementary properties of addition and multiplication, so it is convenient to first express divisibility in terms of multiplication. Note that a natural number x is divisible by a natural number y if and only if x is equal to y times k for some natural number k. Using the definition of divisibility, we can now define the unary predicate p on natural numbers that we wish to establish with induction. To this end, denote for all natural numbers n by Pn the existential quantification there is a k such that n cubed plus 2n is equal to 3 times k. Note that, indeed, the existential quantification at the right-hand side of the definition symbol is a unary predicate. It has a free variable n. Now our goal is to establish that for all natural numbers n, we have Pn. Let's start by recalling the principle of induction. To prove that P holds for all natural numbers, it suffices to prove that P holds for the starting number 0, and that it satisfies the pass-on property. For all natural numbers I, if P holds for I, then P holds for I plus 1. Let's start with the base case and prove that P holds for 0. To figure out what we need to do for that, we should look at the definition of the unary predicate P. We get P0 by replacing n by 0 in the existential quantification. In other words, we should prove that there exists a natural number k such that 0 cubed plus 2 times 0 equals 3 times k. Note that the left-hand side of the equation, 0 cubed plus 2 times 0, equals 0, which clearly is equal to 3 times 0. Thus, setting k to 0, we find that there exists a k such that 0 cubed plus 2 times 0 equals 3 times k, and therefore the proof in the base case is now complete. We proceed with the step case, in which the goal is to establish the pass-on property. Standard logical reasoning yields the declaration of a positive natural number I, for which it is assumed that P holds. And then the goal is to prove that P holds for I plus 1. Let's first consider Pi. We use the definition of P, replacing n by I, to find the existential quantification abbreviated by Pi. With an application of existential quantification elimination, we get a witness for the existential quantification. Some natural number k satisfying I cubed plus 2i equals 3 times k. We shall refer to the equation I cubed plus 2i equals 3 times k as the induction hypothesis. The goal is then to prove that P holds for I plus 1. That is, we need to prove that there exists a natural number L such that I plus 1 cubed plus 2 times I plus 1 equals 3 times L. Let's consider the left-hand side of the equation, I plus 1 cubed plus 2 times I plus 1, and do some elementary mathematical reasoning. First, we compute I plus 1 cubed. Then, by rearranging terms, we create an opportunity to apply the induction hypothesis. The induction hypothesis allows us to replace I cubed plus 2i by 3k. This is a significant step in the right direction, since our aim is to show that there is a factor 3 in the expression I plus 1 cubed plus 2 times I plus 1. We can now take out a factor 3 from the second term, and then write the expression as 3 times k plus I squared plus I plus 1. Note that, since k and I are both natural numbers, so is k plus I squared plus I plus 1. Thus, we have now proved that I plus 1 cubed plus 2 times I plus 1 equals 3 times some natural number, and therefore we have now proved P I plus 1. Our derivation is now complete. Let's also present the proof in natural language. The goal is to prove that n cubed plus 2n is divisible by 3 for all natural numbers n. We announce that we will do so by induction, and hence will prove a base case and a step case. In the base case, the goal is to prove that 0 cubed plus 2 times 0 is divisible by 3. This is achieved by showing that 0 cubed plus 2 times 0 has a factor 3. In the step case, the goal is to prove for all natural numbers I, if I cubed plus 2i is divisible by 3, then so is I plus 1 cubed plus 2i plus 1. So we declare an arbitrary natural number I, assume that it is divisible by 3, and set out to prove that then also I plus 1 cubed plus 2 times I plus 1 is divisible by 3. First, we conclude from the assumption that I cubed plus 2i is divisible by 3 that there exists a natural number k such that I cubed plus 2i equals 3 times k. Then we apply elementary mathematical reasoning and the induction hypothesis to write I plus 1 cubed plus 2 times I plus 1 as 3 times k plus I squared plus I plus 1, thus showing that it is divisible by 3. Here you see the proof, using induction, that n cubed plus 2n is divisible by 3 for all natural numbers n. Note that the important elements of an inductive proof are all there. The proof starts with an announcement that induction will be used. There is a base case, in which the statement is proved for the starting number 0. There is a step case, in which the goal is to establish the pass-on property for the statement. The step case starts with the declaration of some arbitrary natural number I, for which the statement is assumed. This latter assumption is the induction hypothesis. And there is an application of the induction hypothesis. We have proved a universally quantified statement involving divisibility using the principle of mathematical induction. The reason why mathematical induction was a convenient proof technique here can be summarized with the following equation. It relates the question as to whether n plus 1 cubed plus 2 times n plus 1 is divisible by 3 to the question as to whether n cubed plus 2n is divisible by 3. Indeed, you may remember that this relationship was the crucial insight that allowed us to establish the step case. This concludes our third example of a proof by mathematical induction, involving the notion of divisibility.